Inverse function. This is a continuation of our lessons in functions. This is chapter 1, differential calculus, fundamentals and applications. So these lessons are designed for non-math majors. Let us go back to our understanding of a function. Given sets x and y, a function f assigns the elements of x to exactly one element of y. To assign the elements of x to exactly one element of y is another way of saying that you will assign the elements of x to a unique element of y. This pairing, this mapping produces a set of ordered pairs, okay? We call x as the first coordinate and we call y to be the second coordinate. And so this is the diagram of what is taking place in a function. We have set x and x has elements. We are going to pair it to exactly one element y in set y. Y is sometimes called as the image of x under f. And x is sometimes called as the pre-image of y under f. So I will show you a few diagrams of what functions do to a set. So this one is a function defined by 3x plus 1. The elements of x, which is the set of real numbers, is going to be paired with the elements of y, which is also the set of real numbers, according to this rule. F of x is equal to 3x plus 1. So in this case, 3 is paired to 10 because 3 times 3 plus 1 is 10, and 5 is paired to 16 because 3 times 5 plus 1 is 16. Now the pairing can happen in this way. This is also a function, a quadratic function in particular. So 3 is paired to 8, but negative 3 is also paired to 8. And then 5 is paired to 24. Again, this pairing is done according to this rule. G of x is equal to x squared minus 1. This one is another function. It is a constant function. The set of real numbers is paired to one element in the set of real numbers, which is 10. So h of 3, okay, 3 is paired to 10, negative 3 is paired to 10, 5 is paired to 10, so on and so forth. So this pairing produces a set of ordered pairs. So the first coordinate came from set x and the second coordinate came from set y. Now, this is what we shall do. We will invert the pairing. We will interchange the pairing. So in F inverse, what I'm going to do is this pair here will become this pair. 10 will become the first coordinate and 3 the second coordinate. Here, okay, I will invert this. 16 will become the first coordinate and 5 is the second coordinate. I will do the same for sets G and H. So you call this F inverse, G inverse, H inverse. This is the question. F, G, and H are functions. But what about F inverse, G inverse, and H inverse? Well, let us see. So here, this is how the pairing is done. F of x is equal to 3x plus 1. Under F inverse, okay, 10 is paired to 3, 16 is paired to 5. Now, let us look at the second function, g of x. So, g of x is defined as x squared minus 1. Now, g inverse, if we shall look at g inverse now, 8 now is paired to two elements, 3 and negative 3. 24 is paired to 5. What about H inverse? Under H inverse, 10 is paired to 3, negative 3, and 5. So which of these three pairings or which of these three inverses are functions? G inverse and H inverse are not functions, okay? These are not functions because they do not adhere to our definition of a function. A function is a mapping that pairs the elements of the domain of the function to a unique element in set Y. But this is not the case for G inverse, okay? We are pairing 8 to two elements, 3 and negative 3. Here, we are pairing 10 to 3 elements. So these two inverses, G inverse and H inverse, are not functions. This, however, F inverse is a function. What then is an inverse function? So given two one-to-one functions f and g, if, okay, so this is our notation for function composition. If this function composition, when applied to x, is equal to x, and if you interchange the composition and you applied it to x and the result is x, then f and g are inverse functions of each other. And if f is a one-to-one function, its inverse, which is also a function, is denoted by this. I will go back to this one-to-one function in a later slide, but for now, I want to go back to this. This is function composition, and that was the last topic we spoke about in the previous video. So a function composition, okay, G circle F and F circle G, they are a sequence of functions, okay? So what you do is you apply F on X, and then you apply G on the result of F of X. So it's a sequence of functions that you apply to X, then to the result of F of X. What this definition means is if two functions, G and F, are inverse functions of each other, when you apply it to an object, to an input, okay, sequentially, the result is going to be the original input. It's like the two functions will return the result to itself. So something like this. So F and F inverse are inverse functions of one another because when you apply F on 3, the result is 10. And then when you apply F inverse on 10, the result is 3. So applying the function and its inverse function returns the output to the input. Okay, so that is how we can say it. It's the same with 5. And it's the same when we started with F inverse. So using F inverse of 16 is 5. And then when we apply F to 5, the result is 16. And so that is what's happening here in this function composition. The function composition between two functions which are inverse functions of one another. If you apply the function composition on an input, the output is going to be itself. Okay, so let us now go back to the idea of one-to-one functions. Maybe you have heard of it in passing in your other subjects when you were in senior high. So given a function whose domain and range are d sub f and r sub f respectively, the function f is one-to-one, or it is a one-to-one function if and only if each element in the range of your function has only one or a unique pre-image in the domain of your function. So this one, for example, function g is not a one-to-one function because this one, okay, so this is the image of 3 under g. But the pre-image of 8, okay, the pre-image of 8 under g are 2, 3, and negative 3. And so the pre-image is not unique. G inverse is not one-to-one. It's the same with this. So h is a function from x to y. 10 is an element of the range of your function h. But the pre-image of 10 under h is not unique. It has 3 pre-images. H here is not a one-to-one function. This one, however, is a one-to-one function because the elements of the range of the function f, each of them has only one and only one pre-image. The pre-image of 10 is 3, the pre-image of 16 is 5. F here is a one-to-one function. How can you tell if a function is one-to-one based on the graph of your function in the xy plane? If any horizontal line meets the graph of a function at more than one point, then the function is not one-to-one. This is another way of saying it. Okay, so you are given the graph of your function. If any horizontal line meets the graph at no point or only one point, then the function is one-to-one. For example, is this a one-to-one function? Yes, it is a one-to-one function because any horizontal line drawn on your xy plane will not meet the graph in more than one point. Okay, so this function is a one-to-one function. How about this? Is this a one-to-one function? F of x is equal to the square root of 4 minus x squared. Well, it is not, okay, because this horizontal line meets the graph of your function at more than one point. This function is not one-to-one. How about this one? This one is a linear function. F of x is equal to x minus 1. Yes. Any horizontal line drawn on your xy plane will meet the graph only at one point. This function is one-to-one. This is the graph of your cosine function. Okay? It is not one-to-one because the horizontal lines that are drawn in this region will intersect the graph of your cosine function at more than one point. The cosine function is not one-to-one. Now, how about this? So this is a portion of the graph of your cosine function. F of x is equal to cosine of x, where we are restricting our x's in this interval, 0 to pi. Now, is this a one-to-one function? Yes, it is. Because any horizontal line drawn on the xy plane will not intersect the graph in more than one point. So this is telling you something. If you have a function that is not one-to-one, such as this, f of x is equal to cosine of x, we can make it one-to-one by restricting the domain. In which case, we can produce an inverse function for the cosine function for as long as we will observe this restriction in the domain of your function.